So, welcome to a lesson which will explain experiment L5, which is an experiment to measure the wavelength of light using a diffraction grating and a spectrometer. So the experiment, find the experiment in your notes. You've already looked at lesson 6, part 4. That'll be important. That more or less explains everything. So just quickly go through it again in your notes. You shine monochromatic light through a collimator onto a diffraction grating, which is on a turntable. The light passes through the diffraction grating and you get these bright images which are formed. You can view those bright images using your telescope, which you can rotate left and right. There's a vernier scale on the turntable that will allow you to measure the angles. For example, there we have angle θ1. So, the way you would do this experiment, the method is set out there very simply. You've got a table of results. Let's have a look at that table of results in detail. So first of all, what you're going to do is you're going to go to order number 1, which are the first order images. You're going to rotate your telescope onto the first order image on the left and the first order image on the right. You're going to measure each angle. They should be approximately the same, but they might be a little bit off. So you'll get the average θ for n equal to 1. Then you may do it for n equals 2. You'll measure the reading left and right, and you'll get an average. Now you're going to work out the wavelength using your diffraction grating formula. Lambda is equal to, n lambda is equal to d sine θ. You want lambda, so lambda is equal to d sine θ divided by n. You're actually going to get two values of lambda. One for n equal to 1 and one for n equal to 2. But of course, each lambda will be the same, so then you'll get the average. So for example, the first wavelength lambda 1 will be d sine θ divided by 1, where θ is the average angle for n equal to 1. And then you'll find the second wavelength using the values for n equals 2. In this case, n will be 2 in your formula. You'll get two values for lambda, and then you can get the average value for the wavelength by adding your two wavelengths together and dividing by 2. Look, the best way to explain this, of course, as usual, is to do a leaving cert question. So let's get the leaving cert question, which is on the next pages in your notes. So if I scroll down in our notes, I've got a nice leaving cert question, leaving cert 2018, experiment L5. So it says, a student used a narrow beam of monochromatic light at a diffraction grating to determine lambda, the wavelength of monochromatic light. The following data were recorded. Phi, now read this carefully, is the angle between the two first order images. Is 34.1 degrees. They also give me the grating element. Do you know what the grating element is? It's the number of lines per something. Here we have 500 lines per millimeter. Anyway, we'll deal with that in a few minutes. The first part is, as usual, draw a label diagram of the apparatus. And they also want you to describe something, how the angle between the first two images was obtained. Okay, so you've got to be able to draw this diagram, which we explained anyway in lesson 6, part 4. So here's my label diagram. 6 marks for the label diagram. Get all the important parts in. Get your collimator in. Get your diffraction grating in. Get your telescope in. Get your turntable in. Get your monochromatic light in. So once everything is in there, you've got your full 6 marks. Then they're saying describe. So you've got to say a few words. And they're asking to describe how the angle between the two first order images was formed. The angle we're talking about is the angle between n equal to 1 up there and n equal to 1 down there. And that angle we're calling phi. The phi, you can see, is made up of 2 θ because the angle above and below should be the same. So what do I need to say to describe? Well, you're going to measure θ for n equal to 1 to the right. So measure θ for n equal to 1 to the right. You've already got theta written down in your diagram. Measure theta for n equal to 1 to the left. And then subtract the angles to get phi. So if you subtract those two angles, whatever that angle is and that angle there is, subtract them, get your value for phi. So 9 marks for that description, 6 marks for your diagram. Right, moving on to the question. We're now been asked to calculate the wavelength of the beam of light. So here's a straightforward application of your formula. N lambda is equal to d sine theta. So what have I got? The information I have is that the grating element is 500 lines per millimeter, and phi, that's the angle between the two first order images, is 34.1 degrees. Well, the formula you're going to use, so write down your formula, and you will get marks, of course. N lambda is equal to d sine theta. So I want to work out lambda. Well, we are talking about the first order images, aren't we? So I know that n is equal to 1. Now remember, phi is the angle between the two first order images. So if I want theta, which is just the angle of n equal to 1 on the left or the right, well, I'm going to divide the 34.1 degrees by 2. And that will give me an answer of 17.05 degrees. I also want to find d. You know what d is? It's the distance between any two lines. And you've got a technique for doing this. So what's d? Well, if there's 500 lines per millimeter, the distance between any two lines is 1/500th of a millimeter. I'll turn that millimeter into its power of 10, which is 1/10 to the power of minus 3 meters. So you've done that calculation many times before. So put that into my calculator. Fraction 1/500th multiplied by 1/10 to the power of x minus 3. And I get an answer of 2/10 to the power of minus 6 meters. So I now have d is 2/10 to the power of minus 6 meters. So now I'm ready to work out lambda. So writing that formula in terms of lambda, lambda is equal to d sine theta divided by n. So d is 2/10 to the power of minus 6 by the sine of theta is 17.05 degrees all over 1, which I don't have to put in, but I'll write it anyway. So put that into my calculator. 2/10 to the power of x minus 6 multiplied by the sine of 17.05 degrees, close bracket, and I get, say, 5.86 by 10 to the power of minus 7. 5.86 by 10 to the power of minus 7 meters. That's my wavelength. So a very straightforward calculation. So let's return to the question and look at the next part. The next part of the question is saying to me, describe the effect of the size of the angle phi, the angle between the two first order images, if the diffraction grating was replaced with a diffraction grating of 80 lines per millimeter. Hence determine which grating would give you a more accurate result for lambda, and they want you to explain or justify your answer. They're also asking me, what would the student observe if the monochromatic light was placed with a source of white light? Okay, so last few parts. So what are we saying? 500 lines per millimeter, that was the diffraction grating we were using, and that's now turned into 80 lines per millimeter. What happens to your value of phi? There's my diffraction formula. Well, what's happening here? What's happening to the value of d? Remember, d is the distance between any two lines. If you've got 500 lines per millimeter, D is going to be much smaller, isn't it? Compared to having 80 lines per millimeter. There's going to be a bigger gap between the lines. So therefore, I can say, by changing to 80 lines per millimeter, D will go up. What happens to theta? Well, let me write that formula down in terms of sine theta. So sine theta is equal to n lambda divided by D. What happens if D goes up? You divide by a bigger number. Well, the overall number will therefore get smaller. And that means sine theta gets smaller. As sine theta gets smaller, theta gets smaller. So theta goes down. And of course, phi is made up of theta plus theta. So what happens to phi? The answer is phi gets smaller or decreases. You just have to write the answer and they'll give you the 3 marks. But you know, how am I going to find the answer? I need a method of working it out. And we looked at that method. We looked at that method in one of the lessons. So know how to work it out. So phi gets smaller. Now they're saying, which grating gives a more accurate result for lambda? Well, when you're dealing with bigger angles, you'll get better results. So what diffraction grating gives me a bigger angle? Well, it's the 500 lines per millimeter. So which grating gives a more accurate result? I would say the one 500 lines per millimeter. That will give me the better result. The 3 marks for saying that. And they want me to justify my answer? Well, we can say bigger angles What does that mean? That means, and we use this quite a lot, that means a smaller percentage error in your result, which is the wavelength. That's a more accurate result if it's got a smaller percentage error. So that's my justification for that, and that's 3 marks. And the last part they're asking me, what would happen if that monochromatic light was replaced with white light? Well, you know what happens. You end up getting rainbows or spectra. So you can say spectra are obtained. You know they're obtained at n equal to 1, n equal to 2, n equal to 3, but not at n equal to 0. I don't think they're really asking that anyway. They're not asking that. Why do you not see a spectrum at n equal to 0? Spectra are obtained. That's fine for 4 marks.